Mathematicians formulated the following 4 properties and found a lot of conclusions which all hold if only these 4 properties hold. So it's a very general concept, but we need it not that general. In our context, we will need only our n vectors, so 2-dimensional, 3-dimensional, or n-dimensional vectors, not more. What are these properties? These are these 4 properties, and they are really simple. Let's have some examples. Being in a room together with students, I will ask them, please give me a and a b and an x vector, whichever you want, and maybe you will tell me 2 times 3 times 2, 7. So now we check for that example if this is really equal or not. And this is very easy to check. How can we check that? This is 6, 21, and so we get 12, 42. And now let's check that variant. So we have 2 times 3 times 2, 7, and now we have a 6, and that means we have 12, 42. So it's true for this example, for this choice of numbers and this choice of vector, but is it true in general? And it is. Sure it is, because the way we multiply, this is a direct consequence of the rule for real numbers, because the multiplication means doing that in every coordinate, so it's a direct consequence. So absolutely no problem. Second, give me a number and 2 vectors, and then we will test. Maybe you will give me the number 2 and the 2 vectors, these. And now let's test if, let's check. Here we have a -1, 10. And so we get we have a 2, 20. Yes, now it's correct. Okay, here we have 4, 14. And here we have -2, 6. And adding these two, we have 2, 20. And this is indeed the same. So very easy. Let's check the third one. Please give me 2 numbers and 1 vector, let's say, and let's check if this is. And indeed, this is true. And the fourth is very simple. 1 times some vector, let's say 7 minus 4, is indeed 7 minus 4. So for these examples, this is true, and for every other choice of a, b, and vector x, y, it will also be true. That's really easy. The set of all functions defined on R is also a vector space, and also these properties hold, and a lot more examples. As I said, we need only Rn, so we don't want to spend much energy on examples outside Rn. Okay, and now we want to talk about a vector norm. A norm is something you put in a vector and it will return a number. And if you put in some vector, the number must be a number more or equal to 0. There are never negative answers. The number 0 is only returned if the 0 vector is the input. If and only if, and mathematicians write that with if and a second if. That means if and only if. Okay, this is one property of a vector norm. The second property is, okay, this is a concept on a vector norm, and later we will deal with several norms, so we have to understand that concept. Let's start with the typical vector norm, that's the Euclidean norm. What is the Euclidean norm? The Euclidean norm, please give me some vector. Maybe you give me 2, 5, minus 3. And the Euclidean norm is written by an index 2 here. So what is the Euclidean norm? It's the length of that vector, and that is the square root of the squares of the entries. So 2 squared plus 5 squared plus minus 3 squared. And this is 4, 25, and 9. So this is square root of 38. So that's how the Euclidean norm works. And now let's check if it's really a norm. Does it really satisfy these three properties? Let's start with the first one. The answer here, square some number, you get a positive number or a 0, but never a negative number. Add to that once more a positive number or a 0, but never negative. Add to that a positive number or a 0, but never negative. So this sum is either 0 or more than 0. And then it's possible to take the square root out of that, and the answer is some number 0 or more than 0. This is square root a squared, b squared, c squared, and the answer is indeed at least 0. And 0 is a possible answer, but only if the input is 0. If one entry is not 0, you will get a positive number, and then the square root of that will not be 0. So this is indeed true. Okay, so V1 holds. And now let's check V2. So please give me an example. Maybe you give me the norm of that is square root of 16 plus 100 plus 36, which is square root of 152. And we can factor that 4 times 38. 4 times 30 is 120. 4 times 8 is 32. So this is indeed true. And so we can say this is 2 times square root 38. And now let's compare that with absolute value of 2 and the Euclidean norm of 2, 5, minus 3. Absolute value of 2 is 2, and the Euclidean length of that vector we had already, and this is square root 38. And so this is indeed true. And it's not so hard to prove in general. We can prove that what did we do? We did simple analysis, multiply, expand that, so you get that. Everywhere there's a squared, so we can factor out an a squared. And now the rule for the square root is, and the square root of the square is the absolute value of a, and this is nothing else than x1, x2, x3, 2. So we proved in general that this is true. And now V3, please give me an example. Please give me 2 vectors, and maybe you give me 2, 5, minus 3 plus 1, minus 7, 8. And now let's check. Here result is 3 minus 2, 5. And so the 2 norm is 25, 38 again. That's, I did not intend it that it's again 38. This comes from the very special interaction of these vectors. So okay. And now let's check if this norm and that norm, let's check that. This is square root 38. And this is at least 0, so this is indeed true. In this case, it's square root of 114, and so this is indeed true. if you want to prove that in general, this is not so easy to prove. Then you have to compare that, and this is square root of, and you have to compare and to understand why this is always less or at most equal to that. This proof is not very nice, it's a very long one, and it's not much fun. So I don't want to show that here. But what is the picture? The picture is very easy. If this is x and this is the y, then this is x plus y, and the length of x plus y is never more than length of x plus length of y. It is possible that they are equal if that is x and that is y. Then the length of x plus y is the same as length x plus length y, but it's impossible that the length of that line is longer than the sum of these two lengths. So it's obvious from that picture, but not so easy to prove. Okay, that's the Euclidean norm. Okay, and now the maximum norm as an alternative to the Euclidean norm, and we write it that way with an infinity instead of the 2. And what is the maximum norm? The maximal absolute value of the coordinates. So let's have an example. 2, 5, minus 3. The maximum norm is which number? It is 2 compared to 5 compared to 3. What was the largest number? It was 5. So the answer is 5. Let's check if our three properties are true. The answer is always a number which is the smallest number possible. Because of the absolute values, the smallest number possible is 0, and that means that the answer is indeed more or equal to 0. And is the 0 a possible number? Yes, it is, but only there is one coordinate not being 0, then the absolute value of that number is more than 0, and so the maximum norm is a number more than 0. So V1 is indeed true. Let's check V2. So give me an example. Let's say 6 times 2, 5 minus 3. This is 12. 30 minus 18. What is the largest number? This is 30. Compare 12 and 30 and plus 18. Largest number is 30. So this is true. And is it indeed absolute value of that times this is 6, this is 5, and so it's indeed equal to that, and that is true for all numbers and all vectors. That is easy to prove. Why? Because the largest number here in that vector stays being the largest number. Doesn't matter which number you multiply with. The largest number, if it was in the second coordinate, it will be in the second coordinate again after the multiplication, and then the maximum norm yields the number which we need. So V3. So give me an example. Maybe you give me 1, 5 minus 3 plus 7 minus 6, 1. And then we get. And what do we get if we take the maximum norm of that plus the maximum norm of that? We get 5 plus 7. So this was one example. Then I will ask my students, please give me an example where we have equal. What do you have to do if I want to get an equal? So which vector can I use here that we get an equal? So please think about that. What do we need? For example, we need minus 6, 7, 5. And then we have a 12, and let's compare. We have 5 plus 7, so we have an equal. What is necessary to get an equal? We need the largest element in the same coordinate and we need the same sign. So if here the largest element of the first vector is in the second coordinate, then the largest element of the second vector needs to be also in the second coordinate, and we need the same sign. If this is a +5, this has to be a +7, and if this was a -5, then this has to be a -7. You can also prove that, but we don't want to do that. What did we do so far? We introduced the term vector space and the term vector norm, and there are a lot of properties, and being a mathematician, that is how things get started. Being an engineer, maybe you say, okay, what is that good for? What will happen in the next videos? We will talk about matrices. And on matrices, you can also define norms. That's what we will do in the next video. And then we will talk about consistent norms. So norms on a vector, norms on a matrix, and vectors and matrices can interact. And so there's a term consistent norm. And then we will formulate a very, very famous theorem, the Banach theorem. It will tell us something about fixed points, and then we will reformulate our Gauss-Seidel algorithm, or better, the Jacobi algorithm, and then we will use Banach fixed point theorem and these things which we are doing here, and then we can prove that Gauss-Seidel, or better, we will prove that Jacobi, the Jacobi iteration, will converge to the solution of the system if the matrix is diagonal dominant. That is what will happen, and that is why we need what we did in that video. So this was a start, and it will need a lot more theory, but we will do that theory, and in the end we will get a proof, and that is what we are looking for.